Welcome to week 8, lecture 2, work and energy. So this is the start of a new chapter and also kind of a new section of the course. So this is the first 3 parts of chapter 11, so 11-1, 2, and 3. We're going to talk about work done by a constant force. We're going to do an example problem, and then we're going to talk about power. So work is the effort needed for a specific force to move an object a specific distance. The work given by the variable capital W is the force times the distance traveled, which is S here. The units of force are Newton meters, which is also its own unit, joule or joules, and that's given by a capital J. Only the parallel component of the force does work on the system. So when the object is on an incline like this, or the force acts at an angle that is different than the motion, we have to take into account the angle between the force and the distance traveled or the motion. So here the block is pushed up with a horizontal force. But the distance S is along the plane, so we need the component of the force that's also along the plane, which is cosine. So work is the force times the distance times cosine of the angle between them. Let's look at some examples of work. In this one, we have a block pulled by a rope, going distance D, and the force acting on the rope is horizontal, and so is the motion. So the angle between them is 0. Cosine of 0 is just 1. So we end up with work equaling the force times the distance, and this gives us positive work. We have another example. In this one, the force is applied at an angle, but that angle is less than 90 degrees. So the work done is the force times the distance times cosine of that angle. And cosine of an angle of less than 90 degrees is positive. So the work done will be positive in this example. Then we have a force that is straight up, but the motion is still horizontal. The angle between the force and the motion is 90 degrees, and cosine of 90 is 0, so no work is done. So if the force is perpendicular to the motion, like entirely perpendicular to the motion, no work is done. Now, in this example, the force is at an angle greater than 90 degrees. So the force is kind of in the partially in the opposite direction of the motion. And cosine of something great of an angle greater than 90 degrees is negative. So the work done is negative. And then finally, in this example, the force is anti-parallel to the displacement. The force is to the left and the motion is to the right, making the angle between them 180 degrees. Cosine of 180 degrees is -1. So the work done is negative. And I want to go briefly back to this one and just mention one way beyond thinking of the angles to help you figure out if the work done is positive, negative, or 0 is to look at what direction the force acts versus what direction the motion is. So if the force acts in the opposite direction of the motion, the work done is negative. If they act in the same direction, it's positive, and if they are perpendicular, it is 0. So that's just one kind of trick to keep in your mind. So let's do this sample problem. I'll read it first. A child pulls a 5.6 kilogram sled a distance of 12 meters along a horizontal surface at a constant speed. What work does the child do on the sled if the coefficient of kinetic friction is 0.20 and the rope makes an angle of 45 degrees with the horizontal. Okay, so we're gonna just start by drawing a free body diagram for the sled. So we have our typical coordinate axes, and then we'll start with this tension force, T, angle of 45 degrees. Then we have the weight force, we have the normal force, and we have the kinetic friction force that acts in the opposite direction of our motion. And I'm saying our motion is that way because that's the direction the rope is being pulled. And we're asked what work the child does to pull the sled. And so that's going to be the tension. Or the force of that will be the tension. And we want to also break up the tension into our X and Y components as well. And I will write those right here. Ty is the tension times sine of theta, or sine of 45. And Tx is the tension times cosine. So let's do our sum of forces. This is all stuff we're familiar with. Sum of forces. And I think it says constant speed. So there is no acceleration. So we'll start with sum of forces in the y direction, which is 0. And our positive forces in this direction are normal plus the y component of the tension minus the weight force. And then the sum of forces in the x direction, also 0. And this one is the x component of the tension minus the kinetic friction force. Yeah, cool. So now what we want to find, like I said, is this T, the tension. We have two equations, and I think we should be able to relate them to each other. Let's do a little moving around of things. So generally, I think we're pretty familiar with the fact that friction is the coefficient times the normal force. So let's figure out what the normal force is in this situation. So I'm going to add the weight to both sides and subtract the y component of the tension from both sides. So we end up with the weight minus the y component of the tension, which is also mg minus t sine theta. Okay, so we have a value for the normal force. Let's rearrange this equation, and I'm just going to add the kinetic friction to both sides. So we end up with t cosine theta equals mu k normal force. So we can plug in those two here. So let's do that. We have t cosine theta equals mu k times mg minus t sine theta. So again, we're solving for the tension here because before we can find the work, we need to know the value of the force. So I'm going to distribute this mu k, mg minus mu k t sine theta, and then I'm going to add t sine theta to, or mu k t sine theta to both sides because I want to get tension all by itself. So t cosine theta plus mu k t sine theta equals mu k mg, and then I'm going to factor out the tension from these, so it's just tension times cosine theta plus mu k sine theta. That way I can divide that on both sides, and I have solved for my tension. So tension equals mu k mg over cosine theta plus mu k sine theta. Now we can plug in our numbers. So mu k is 0.20. The mass is 5.6 kilograms. G is 9.8 meters per second squared. We have cosine of 45 plus 0.20 sine of 45. This gives us a tension of 12.9 newtons. Okay, but that's not the answer to the question. That is just the force itself. So we continue. I am going to, it's not really a free body diagram. I'm just gonna put our force and displacement vectors in one place. So we have tension and we have theta. And then our displacement is just horizontal displacement. And then the work is FD cosine of theta. Start with the work part, W, work. Force, displacement, cosine of the angle between them. We know all of those, so we can just plug them in. So we have a force of 12.9 newtons, displacement of 12 meters, and cosine of 45 degrees. So this gives us the work done of 109 Newton meters, or also 109 joules. So let's just quickly go back through what we did here. We did what we should be comfortable and familiar with, which is we drew a free body diagram of the situation. We got our forces, and we just solved for the tension. That was the thing we wanted, so we solved for it. And then we just looked at how the tension and displacement were related to each other, just to make sure we knew what we were doing. And we got that the work is the force times displacement cosine of theta, which we plug everything in, and we got 109 joules. Let's go back to the slides now. So another thing to note is that work is a dot product, which is the relationship between two vectors that results in a scalar. So work is a scalar, not a vector. It doesn't have a direction. But force and displacement are vectors. And so this relationship we have here of from the equation of work equals the force times the displacement times cosine of the angle, that comes from dot product. And if we have a more complicated situation where we have extended vectors of these, so like if the displacement wasn't in just one direction, so let's say we have two full vectors, then the dot product is just the sum of the components multiplied by each other. So ax times bx plus ay times by plus az times bz. So just for clarity. Now, power is the rate at which work is done. The average power is given by the work divided by the time over which the work is done. The instantaneous power is the time derivative of the work done. Power is obviously given by this capital P. This is Bandit. He doesn't want to let me finish this lecture. And the units of power are watts or joules per second. If we expand out the derivative, we can get another relationship for power, which is the force times the velocity. So this is just another equation that shows us what the power is, or the work done over time. And you'll find actually in physics that there's a lot of different equations for power. So just a heads up. This is the power we'll refer to in like mechanics this quarter. In the future, you will also have lots of different equations for power in electricity and magnetism. So just heads up. So you're just getting familiar with it now too, is you have 3 different equations for power. Okay, that is everything. Have a great day.